Net force. Let's look at the left side of this equation first. Sigma F. The Greek letter sigma means the sum of. Sometimes sigma F is written as sigma F net or just F net for net force. In both cases, all of the forces need to be summed up as vectors. The arrow above F indicates that force is a vector. The arrow isn't always written, but remember it is there. It means that when forces are added, they are added as vectors. Forces have direction and they can cancel out. A 5 kilogram object is being acted on by a 20 Newton force to the right and a 30 Newton force also to the right. What is the net force acting on the object? First, draw a free body diagram. We will discuss these in more detail later, but for now, follow these simple directions. Free body diagrams consist of a dot representing the object and arrows representing the forces. The direction of the arrows represents the direction of the forces, and their length is roughly proportional to their size or magnitude. The first force acts to the right with a magnitude of 20 newtons. So we draw from the dot, we draw an arrow to the right. The second force, F2, acts to the right also with a greater magnitude of 30 newtons. So we draw a second arrow to the right, but it's slightly longer than the first arrow since the first one was just a 20 Newton force and this one's a 30 Newton force. To add vectors, you move the second vector so that it starts where the first one ends. So just pick up the vector, move it over here. So the tail of the second is going to be at the tip of the first. The sum is a vector which starts where the first vector starts and then ends where the last one ends. So here we have our net force goes from the dot all the way to the end of the second vector. These free body diagrams are critically important to our work. Once done, the problem can be translated into an algebra problem. We will define this way to the right as positive, the positive direction. So we interpret the diagram to read net force equals F1 plus F2. Plug in the numbers, and both of these are going to be positive numbers since they're both pointing in the positive direction. Therefore, the net force is 50 newtons to the right. Now let's look at the right side of our equation, ma. Mass is a scalar. It does not have a direction, but acceleration does have a direction. It is a vector. The direction of the acceleration vector is always the same as the direction of the net force vector. Acceleration does not say anything about the direction of the velocity or displacement. It only tells you how the velocity is changing. In this problem previously, we found the net force on the object to be 50 newtons to the right. Now, let's find its acceleration. All right, so A equals net force over mass. Net force is 50. The mass of this particular object is 5. Therefore, it will accelerate at 10 meters per second squared to the right, in the same direction as the net force. What is the net force acting on a 2 kilogram object experiencing an acceleration of 1 meter per second squared? We're going to say that this object is moving horizontally. Maybe it's a book sliding across a desk. F equals ma is true along each coordinate axis. The sum of the forces in the vertical direction equals ma in the vertical direction. In this case, the vertical acceleration is 0, right? This book that's sliding is not accelerating up or down. So the vertical forces add to 0. This means that those forces, the force up and the force down, must be equal and opposite. In the horizontal direction, there is acceleration. So we use F equals ma again, but now we only focus on forces in the x dimension. So that's just the one force, the horizontal force, F3. That equals ma, plug in our numbers, and we see that force 3 horizontally must be equal to 2 newtons.